Hello everyone! So today we're actually going to start solving some questions on thermodynamics. After in the two previous videos we have learned how to derive ideal gas equations as well as mean square speed equation. If you haven't watched those videos, I suggest you watch first so that you can have a better understanding when solving this question. Okay, let's get started. This is actually from Physics Paper 4, Variant 4.3, October-November 2024, CIE paper. So this is question 3A. Okay, let's start with Roman 1. State what is meant by Avogadro constant. The moment you see the word Avogadro constant, right, I bet you might be thinking you're in the wrong paper because usually Avogadro constant we learn in chemistry in more detail. But based on the equation that we derive about ideal gas equation, we have used the concept of Avogadro constant. So what is Avogadro constant? Avogadro constant is actually the number of particles per unit amount of substance. In chemistry, they might have a more in detail, but this physics is simple as that. Number of particles per unit amount of substance. There you go. Got your 1 mark. Okay, let's move on. Roman 2. State the relationship between the Avogadro constant, molar gas constant, and the Boltzmann constant. Okay. Now, remember we have the formula PV equals to nRT. And we know N is equals to number of molecules over Avogadro constant. So, we can rewrite this as PV equals to N over NA RT. And since NA, which is the Avogadro constant, and the molar gas constant is a constant, we can combine them to form a one constant itself. So how do we do that? We can write it as N R over N A T, where this thing is actually the Boltzmann constant. K equals to R over N A. We've actually derived this in ideal gas equation. So Boltzmann, this is actually Boltzmann constant. So Boltzmann constant is actually equals to molar gas constant over Avogadro constant. You can write it this way, or because they didn't specify which one to make as a subject, so in answer scheme they'll probably write it as NA equals to R over K. Not a problem. Honestly, if you ask me, I don't think it's a problem to write it this way also, because they didn't really specify in the question which to write as a subject. As long as you can clearly show the relationship between K, the Boltzmann constant, molar gas constant, and the Avogadro constant, I believe you will get your 1 mark. Right? Okay, now B. Two samples X and Y of ideal gas are both at thermodynamic temperature T. Sample X has volume V, consists of n molecules, each of mass m. Sample Y has volume 2V, consists of 2n molecules, each of mass 2m. Complete the table 3.1 by giving expression in terms of sum or all of n, which is number of molecules, m is the mass, T is the thermodynamic temperature, V is the volume, and the constants in A Roman 2. That means we can make use of the constants of R, NA, as well as K for the quantities indicated. Okay, now this is table 3.1. Okay, let's perhaps draw a bit here. Okay, imagine this is X. So we have a molecule of mass M, volume V, and we have n number of molecules. Okay. For Y, we have molecules of mass 2m, we have 2n number of molecules, and 2v. Okay, let's see. Pressure. How do we express for sample X and Y for pressure? Okay, we know there's a formula PV equals to nRT, but we can't make use of n here because they say we must give it in N or NA, and we know there's something we can use here, right? So we can make use of that. So we can change it. Another way to write it is PV equals to NKT. Right? Okay. So now we want what is pressure. So we make pressure as the subject. Then it's NKT over V. Okay. Alright. So pressure for X. What is the number of molecules? It's actually N. So it's N. K is constant. T is constant because both at thermodynamic temperature T over V. That's about it. How about sample Y? Sample Y, we have 2N molecules. We have K, we have T over what's the volume? The volume is 2V. 2V. You can cut the 2 off, which is basically NKT over V. Yes. Conclusion, X and Y both have the same pressure. Why? Because remember this concept PV equals to RT. This is molar gas constant, right? In order for the in this case, the volume is changing, right? Both have different volume. So if the volume is changing, P and T should be constant. If the volume is changing, so T is constant already, that means your P also should be constant. In other words, it should be the same. This is actually when volume is changing, P and T, which is pressure and temperature, are the same. This is actually Gay-Lussac's law. I am not sure if I'm spelling the name correctly. I hope I am. Gay-Lussac's law. It's one of the ideal gas law. Yep. So yeah, that's how we get for pressure. Next is amount of substance. Amount of substance basically means mole, in other words. So we know mole is equals to N over Na, right? So for sample X, we have N number of molecules, okay? And your Na is constant. For sample Y, we have 2N, because we have 2N molecules, right? 2N molecules over Na. Yep, easy as that. Now, mean square speed of molecules. Okay. Mean square speed, we know there's a formula. 1 over 2 m mean square speed equals to 3 over 2 kt. Am I right? We have actually derived this. So now let's do this one by one. mc square, make the mean square speed as the subject. So when you bring 1 over 2 to the other side, actually these 2 will be gone. You will only have 3 kt. So then you have c square 3 kt over m. So this is actually your mean square speed. This is mean square speed. Oops. Okay, wait. Let me write properly. Mean square speed. Okay. So this is the formula that you will be using. So mean square speed of molecules for X is actually 3 kt over m only, because your mass is m, right? For X, you only have mass m. For sample Y, it's 3 kt over 2m, because your mass is 2m. Sample Y. Be aware of this mass, molecules, they are changing. So you need to see which sample you are looking at. Okay. Alright. Then, for internal energy, okay. This is a very important point. For internal energy, we know the formula. I denote internal energy as IE, kinetic energy as KE, and potential energy as PE. So we know kinetic energy, we have the formula of 1 over 2 mv square. Or, that is a normal kinetic energy, but based on ideal gas, we have derived this formula, remember? 1 over 2 mc square. Then PE, for ideal gas, the PE is actually equals to 0. How do I know it's ideal gas? I believe they've mentioned here. It's actually an ideal gas. Why PE is equals to 0? Because there's no intermolecular forces. Intermolecular forces in ideal gas are negligible. That's why PE is equals to 0. Therefore, your internal energy is just equals to KE. Basically, 3 over 2 NKT. Why is that n? Because usually internal energy, we talk about total kinetic energy. We don't say internal energy just for one particular molecule, right? we talk of it as overall. Why here I didn't add NKT? Because in this formula, when we derive the mean square speed in terms of kinetic energy, because it's kinetic energy, right? In terms of mean square speed, that we can cancel out the n. Because remember, where is that? Let me show you. Remember here, when we derive the formula, we equate these two, we can already cancel out the n. The n is not needed really. But when it comes to internal energy, we have to add n, not only 3 over 2 kT, because we're talking about the entire molecule's kinetic energy, the internal energy of the whole system itself. That's why we have to put 3 over 2 n kT. Don't forget that. Because we did not say internal energy equals to 3 over 2 kT. Here is kinetic energy equals to 3 over 2 kT. Internal energy equals to 3 over 2 n kT, because we're talking about the whole system itself. So, for sample X, it's 3 over 2, is it n? Yeah, it's n molecules, kT. And for sample Y, we have 2n molecules. So it will be 3 over 2, 2n kT, which will basically, because one can cut, 3n kT. This working all, you can actually do on the side, and you can write your final answer here. Do not write your final answer down here, okay? I'm just showing you here. You can do your workings, even these workings here, you can do it at the side. No worries. You write your final answer in the box. Make sure your final answer are in the box. They give you the box for a reason. Okay? Alright. Okay. Now the last one. Very simple one. Hang on, okay? Last one. You're already there. Also, just by understanding, you have obtained your 4 marks. Just nice, right? So, main thing is, understand the concept, understand the formula first. How is it derived? Then you'll be able to do it. Okay? Okay, last one. Let's go. Sketch the variation. Oh wait, this says temperature of sample is now varied. On figure 3.1, sketch the variation with thermodynamic temperature of the root mean square speed of the molecules of gas. Is there a formula that relates root mean square speed and thermodynamic temperature? Of course, there is absolutely one, which is this. 1 over 2 mc square equals to 3 over 2 kT. So we want to make root mean square a subject. So this will be 3 kT. C square equals to 3 kT over m. Root mean square is usually RMS equals to square root 3 kT over m. I should write my square root a bit better. Okay, 3 kT over m. So when you want to compare two variables, the rest of the variables in the equation must be constant. In other words, I want to compare root mean square and the thermodynamic temperature. So, the K, which is the Boltzmann constant, and the mass must be constant. We know the mass of molecules in a system all will be the same, ideally. Boltzmann constant is a constant itself. 3 is a constant itself. So, we can safely say, therefore, root mean square speed is proportional to the square root of thermodynamic temperature. So this shows that we need to draw a square root graph. Okay, so let's go back. So how does a square root graph look like? A square root graph will actually look like this. This is how a square root graph will look like. Basically, a normal square root graph. Common mistake is people would say root mean square speed is directly proportional to thermodynamic temperature. So they might draw a straight line, which is wrong. There's a square root, remember, so do not miss out your square root. The square root plays a big role as well. There's a reason why it's a square root. So don't ignore the square root. Okay, right. That's about it for today's video. We've nicely discussed and unpacked certain formula details and learn how to better understand the question. And especially if you know the formulas, like for this particular question, you will be able to solve it with ease. No problem at all. So make sure you score those 8 marks, okay, at the end here. Don't forget, score those 8 marks. Don't waste it, okay? Alright, that's all. Thank you for watching. I'll see you in the next video. Don't forget to like, share and subscribe if it helps you, and let me know if there's anything that you want me to share in the comment down below. Thank you. Bye bye.